Hello, welcome to a brand new topic in Maths A-level. We are looking at functions, specifically the part involving something called mapping. Now, before we begin, apologies in advance. This is a bit of a definition-heavy sort of area of maths, so we're going to be sort of defining a lot of terms. There's not going to be that much calculation at this stage, but at the same time, this topic is quite good because it does kind of explain some of the oddities of some of the areas of maths that we've kind of just taken for granted before and just had to nod along and accept, whereas this now sort of explains why they are the way they are. Anyway, let's get going. The first thing I should explain is what is a mapping. And probably the most simple way I could put it to you is it's basically a way of defining how two sets of numbers are related to each other, the relationship between them. And then we then give basically some different names to those different relationships, and in those names, the first word in the name refers to what's going on with what we traditionally view as the input values, what later on this topic we're going to more poshly call the domain, and is often therefore the x values for most functions. And then the last word in the name of a mapping is referring to the output values of that function. That's more poshly, more properly called the range, and again, we could mostly, for simple purposes, look at that as being the y values for the sort of purposes of maths that we have to deal with. Okay, with that said, let's look at the first type of mapping, which is called a one-to-one mapping. So, going by the logic we just said, the first word, where it says 1, is referring to x values, and then the last word is referring to what's happening with the y values. So in general terms, this mapping is saying one x value goes with one y value for the points on the function you are looking at. Now, one way we can actually represent this visually is using something called a mapping diagram, which involves having two ovals, like you can see right now. One of the ovals might represent what's happening with the x values. The second one might represent what's happening with the y values. We then sometimes might have dots or points written inside these ovals to represent the particular values for that variable or particular points. And then we can then make connections between the two sets of numbers to show the relationship. So for instance, for a one-to-one mapping, we're saying one x value, one point over here, goes with one of the points over here. And then if you have a different point, it's going with a different point in the y set. And if we have a third point, oh my goodness, that is also one x value going with one different other y value. And so that's going to be the case for all the values in a one-to-one mapping. One x value goes with one y value. Okay, so that's what a mapping diagram looks like, but how does this look like visually if we're looking at graphs? Well, one example of one-to-one mapping is basically any diagonal straight line. So an example I've decided to choose is y equals minus 4x plus 1, and that's because you can pick any point on this line, and if you pick a particular x value, let's say the one here, I can then go to the straight line and find that there's only one point on that entire line where that x value appears, so hence why it's 1 as the first word in the mapping. And then also there's only one place on that line where that has that y value. So the x values and y values are unique for all the points that are on a function that's got a one-to-one mapping. So that's what's going on there. Cool. Another example though is ultimately, it doesn't just have to be straight lines. You can have curves that have a one-to-one mapping. One example could be y equals e to the x. And in fact, this is particularly interesting because it's not just a curve. It's a curve with a asymptote, a horizontal asymptote. And that's fine too. Because although the graph looks like it's getting horizontal over here, it never actually quite does. It gets very, very shallow, a very, very low gradient, but it never goes directly flat. Never gets a gradient of perfectly zero. So that means you're still going up and down wherever you go on the graph, and therefore there's still, for every point on the curve, just one point in that curve that has that x value, and that one point is the only place on the curve where you can find that particular y value. So that is why it is a one-to-one. I can do this for any other points on this curve. Still, that's the only place you'll find that x and y value. Combination. Cool. Next type of mapping is called many-to-one, and we know the pattern now. Many is referring to the x values, and then the last word is referring to the y value. So this is saying in general, many x values go to one y value. Okay, as a mapping diagram, that could look like this. So we could have several different x coordinates, x values, whatever you want to call them, but then we have more than one x value going to that same y value. And there is, to a certain extent, no limit to how much that can happen. So we could have, I don't know, 3 x values all going to the same one y value. Hence why we say many, to make it clear that, however many it is, it's lots of x values going to one y value. But it's worth pointing out that mappings are done on a worst case scenario. So it's worth pointing out as part of a many-to-one mapping, you can have some individual points that are still one-to-one. As long as there are any points in the function that are a many-to-one mapping, the overall mapping of the function is defined as many-to-one. Cool. So yeah, worst case scenario is sort of decides the naming, basically. Then looking at some graphs, probably the most classic example of a many-to-one function would be just y equals x squared. So that is a many-to-one function because we can see that if I pick this x value, I have this particular y value, but that isn't the only x value that leads to that y value. There is another x value that also refers to that y value, and it's the one over there, roughly. So you can see many x values are leading to one y value. So in other words, a way for looking at it is, or looking for it, is to see if there are multiple places to get the same y value. But that's a bit weird because then you get confused between the words for the x values and the y values. So as I said, its best way of viewing it is saying that many x values are then going towards or resulting in one y value. Okay, on to the next category, and well, you can probably start to see that we're starting to replace the word one with the word many to create new mappings, and we can do the same, but just putting the word many in a different place. So we have one to many is another type of mapping. So this time we're saying one x value is going to many y values. Okay, what would that look like on a mapping diagram? Well, a same idea as before, but the roles of the x and the y values are reversed. Now we're taking one x value, and normally we're used to just plugging an x value in and the graph being able to go, right, that is the y value for the x value. But now it's weird because we can plug an x value in, but then there is a choice. There's an unknown choice about which y value it could be linked to. Again, there could be points on the graph where there are just individual points that are technically one-to-one, but because at the moment there's any points on the graph that have multiple y values for the same x value, then we call it a one-to-many. So again, you can have, one x value going to, I don't know, let's ramp it up. Let's say 4 y values for one x value, whatever. There is no limit. Cool. Very badly drawn lines there. Anyway, cool. What is an example of a one-to-many graph? What does that look like? Because that seems a bit weird. And that's for a good reason, actually, because most of the time in Maths A-level, we don't really come across these in Maths A-level, because often the way you are going to create a one-to-many mapping is you start having to not have a y equals anymore. You start having to have a sort of set of operations acting on the y as well. And so one example is y squared equals x. And yes, that is literally just a quadratic, technically reflected in the line y equals x, but visually it looks the same as rotating a quadratic 90 degrees clockwise. So that's the illusion you have got. Funny enough, this also looks very similar, some of you might be wondering, to y equals the square root of x. And that's for good reason, because of course you could try and make y the subject of the formula for this, but in order to do so you'd have to use the square root, which doesn't fully undo a squared, and that's why half the graph gets cut out if you do look at y equals the square of x. Anyway, that will be a conversation though for a later video when we look at inverse functions. But anyway, for the moment, this is y squared equals x, and we can see it's one-to-many because if I pick this x value here, for instance, there are multiple y values for that one x value on the graph. So there you go, one x value going to many y values. To reiterate the point I said earlier, there are some points on these graphs that might not be one-to-many. For instance, the point here is technically a point that's one-to-one. That is the only point on the graph with that x value and that y value. So that is a one-to-one individual value point, but the overall mapping of the function is one-to-many because that's the most extreme thing that's happening in the equation as a whole. Cool. But now we must go on to our final mapping, which is many-to-many. Ooh, it's all happening now. The best way of viewing a many-to-many mapping is to just view it as a combination of both a many-to-one mapping and a one-to-many mapping. And this is actually the easiest way to then check for if many-to-many is happening, because it's some areas on the graph are a many-to-one situation, and then elsewhere on the graph or in the same place there are regions that are situations where we've got a one-to-many mapping happening. And so as soon as you've got the presence of both happening in the same equation, that's when you know it's many-to-many. So what would this look like? Well, we could again label y and x. We can again have some points. Let's put quite a few. So we've got a choice. And as I said, you'll have some areas on the graph which are many-to-one. So we'll have many x values going to the same y value. But then elsewhere on the graph, we might have one x value resulting in many y values, like that. But then, of course, some of these things can interlink. So, I mean, this y value that I've just joined up at the end here could also have a different x value connected to it. So you've got both sort of many-to-one and one-to-many happening at the same time with that y value there. And so, yeah, it's all happening, basically, is a way of viewing it. And so we shall illustrate that to the full extent here. There you go. One-to-many and many-to-one, all happening. What does this look like on a graph? Well, it's actually quite a famous example because it's one you have actually dealt with before, the classic circle, of course. So I've done the example x squared plus y squared equals 25. Why is this many-to-many? Well, if we pick, for instance, this x value here, we can see there are multiple y values that go with that one x value. So this individually is a one-to-many scenario, one x value to many y values. But then elsewhere in the graph, we have multiple x values leading to the same y value. Oh my goodness, that's a very unstraight line. Never mind, you can still probably get the idea and see that many x values are both leading to the same y value. So that's individually a many-to-one. Therefore, this stuff kind of has a similar idea to the previous mappings of this ends up being a many-to-many mapping by a worst-case scenario. You individually notice, oh, there is a one-to-many scenario happening, so at the very least it's one-to-many, but then you notice many-to-one as well, so then, although they aren't all happening all at the same time necessarily in all places on the graph, because there are presence of both of them at all in the graph, you instantly know it is a many-to-many graph, many-to-many equation, if you will. Nice. Okay, and therefore, that is the four mappings we need to know. Very good. Let's look at a couple of examples. There's a bit more I need to tell you about mappings, so do stay tuned. But looking at some quick examples, what type of mappings are these functions going to have? And I've carefully chosen my words there, and you'll see why later. But the best way to do this is just to draw a graph. So for f of x is equal to 1 over x squared, we're not looking at the point where x is not equal to 0 because there is no graph there. That's where the vertical asymptote is. But looking at that graph, that looks something like this. If I badly draw it, there you go. And then something like this. Just an excuse to practice graph drawing skills. A reminder, this is a graph you'd be expected to know off by heart. Even if you've got a graphical calculator, just it's quicker to know these things and just be able to get around to drawing them instantly. Anyway, we can see instantly, well, maybe not instantly, let's have a look what sort of mapping it is, because for instance we could take an x value here, see what the y value is, but then we go, oh wait a minute, that's not the only point on that curve with that y value. There's another x value that's got that y value, so therefore there's many x values going to one y value. Luckily though, depending, no matter which x value I pick, there is only one y value that goes with that x value. So you don't plug an x value in and have a choice of y values to choose from. So therefore, it is just many-to-one. It doesn't include one-to-many at all. So it does just stay as many-to-one. Interesting because, again, it shows, you can have these graphs with curves, with asymptotes, and, that doesn't, it's by itself narrow down fully what sort of mapping it has. B, g of x is equal to negative x squared, and then it has this notation, which basically means x is an element of the real numbers. We'll talk about that more later, but basically, in layman's terms, it means the whole graph, effectively, for real numbers. So if we draw that, reminder, x cubed is one of the standard graphs you're meant to know. The minus in front just means it's been reflected in the x-axis. So in other words, it's upside down, and therefore we're going to have a graph that looks very roughly like this. If I badly draw it, there you go, lovely badly drawn. What sort of mapping does this have? Well, let's take a look. This x value, for instance, only has one y value that goes with it. So instantly we know it's not one to many because you can choose that with any of the x values here. There's not a choice of y values. But, interestingly, there's not really a choice of x values either for the y values, because any point you pick on this curve is going to be unique. It's the only place on that curve where that x value appears, and also it's the only place on the curve where that y value appears. So therefore, this is just a one-to-one mapping. Nice and simple. Okay, the third and final example. Actually, no, I lie. I've got a fourth example of this. Third example of this type, we've got to draw, or find out the mapping, I should say, of this function. And the best way to do that is to draw a graph. So again, using our graph drawing skills, first of all, this is clearly going to be a cubic. It's clearly going to be a positive cubic, because although I'm not going to bother multiplying out the brackets, if you were, you would see we'd have an x times by an x times by an x, which would lead to a positive 1, lots of x cubed, so it's a positive x cubed shape. Then we also know its x-intercepts are at x equals minus 2 and x equals 3 from the brackets, because you could set the equation equal to 0 and solve. That's how I've got those x values. Interesting though, specifically, x equals 3 is a repeated root, which matters because it means the curve is going to bounce off the axis at that point rather than officially crossing it. And then you could work out the y-intercept as well. The y-intercept would be plug x equals 0 into the curve, the equation of the curve, and you'll get 2 times by minus 3 squared, which is going to be 18. So putting all that together, we're going to have a curve that looks something very vaguely like this. Ooh, there you go. Something like that. There you go. And so therefore, that's where 3 is, that's where minus 2 is, and if you really wanted to, that's 18. Worth pointing out that I've made it look like the stationary point is where the y-intercept is. I have no idea if it is or not, and it doesn't really matter for the purposes of this question, so it's just a rough sketch. Okay, now, you might be fooling and thinking, oh, it's 1-to-1, because if we pick a point over here, that's the only place where the x value appears, and that's the only place in the graph where that y value appears. But remember what I said, it's always a case of worst case scenario. So although that point individually is a 1-to-1 mapping, if we pick some other x values or other points on the curve, like for instance this x value, that has that y value, but wait a minute, that is definitely not the only point on that curve that has that y value. There's also this x coordinate, and then, controversially, there's this x coordinate as well, that's also got that y value. So there's 3 x values that all lead to the same y value. So that's many x values leading to one y value, so therefore this is a many-to-one mapping. So that is the answer to that question. Last example, what mapping does this graph have? See, they won't always give you the equation. They sometimes just give you the graph straight up and expect you to just be able to look at it and know. So looking at this graph, be careful. For a start, we straight away know it's got some one-to-many scenarios because situations happening. Because this x value here has multiple points on the graph for that x value, multiple y values for that one x value. So that's a one-to-many situation happening individually. But wait, let's not stop there, because if you also look, this x value has this y value, but also this x coordinate over there here. Sorry if I can say the word here. This x coordinate over here also has that y value. So that's many-to-one also happening in the same graph. So wait a minute, if we've got one-to-many happening as part of the graph, we've got many-to-one happening as part of that graph, then therefore overall this must be a many-to-many graph. And I'm being very careful with my wording there, not saying the word function. As you'll see why now, the last bit of information I need to tell you is what type of mapping you have decides whether we can call something a function. Because with these 4 mappings, we can split them into 2 main categories. There's the top two, one-to-one and many-to-one, and those are important because those two mappings, anything with that type of mapping, is something we call a function. The reason for that is for both of those things, they're sort of situations where you can just plug an x value in and then you just instantly know what the y value is. Sure, there for the many-to-one situation might be many xi's that happen to get the same result, but you don't really care about that. It's still a huge level of certainty. You just plug an x value in, you know the answer. One y value is the answer. That's also linking with other things we've done before, because ultimately any graph that can be rewritten in the form y equals must be one of these two mappings. And again, that's why we call these functions. They're nice equations to deal with because they can all be written as y equals with y as the subject. Whereas the two mappings down here, those are what we'd call things that are not functions. Those are not functions because they have one of these two mappings. So that is something you need to be aware of, the definition of a function. It all just comes down to what type of mapping it has. So if they ask you a question or even give you a graph and go, is this a function, and give reasoning, all you've got to do is identify what mapping it is and then justify, depending on what type of mapping it is, whether it is a function or not. Okay, hopefully you found this video useful. I will see you in a future video.